Hello everyone, welcome to webinar today about DocumentDB best practices using variety of open source tools and utilities. My name is Puneet Raval and I am a database solutions architect at AWS. I spent majority of my career advocating the use of NoSQL databases for workloads that are very dynamic in nature and needs a database that can keep up with it, which is why I'm very excited for the discussion today. For the agenda today, we'll be learning about DocumentDB architecture at high level, which will set a good groundwork for the discussion today on connection management. We will learn why is it important with a quick overview and then jump into some of the best practices. We will also learn how connection management with DocumentDB can be different when you're using Lambdas and when you should use connection pools. We will cover these topics by looking at a Python-based open source project to set up REST APIs using Lambdas and DocumentDB. We will use a popular open source load testing tool called artillery.io. After the demo, we'll just come back here to summarize on what we did today and conclude. Now let's just jump into what exactly is DocumentDB. It is a fast, scalable, fully managed database that can handle JSON workload with ease. It can scale up to millions of document reads per second by scaling compute and storage independently. You can add up to 15 read replicas to horizontally scale read traffic. It automates the hardware provisioning, patching, upgrades, setup, and monitoring. Out of the box, DocumentDB gives you 11 nines of durability with automatic replication, continuous backups, and strict network isolation by being a VPC-only service. With DocumentDB, you can write your application from scratch using the popular MongoDB API, or you can bring your own existing application that are currently running on Mongo. It is built out to be compatible with Mongo 3.6 and 4.0 API. Now let's cover a bit on architecture, which will go very well with our topic of connection management. At the highest level, DocumentDB is architected to separate storage and compute so they can scale independently. When you provision a DocumentDB cluster, service allocates the storage, which is distributed among 3 availability zones, with 2 copies of data in each availability zone. Good thing here is that you don't have to allocate storage or IOPS. The storage layer auto scales and as the data size increases. And it also allocates disk IOPS required to support your workload. On the compute side, you have an option just to create instance, or you can create 3 instances, which is really our production ready cluster that gives you 4 nines of availability in that region. One of those 3 instances would be a primary instance, which takes up writes while others are read replicas. Now, read replicas also serves the requirement of high availability by becoming primary writer in case the primary instance goes down for any reason. Just like EC2 instance, DocumentDB instance comes with certain CPU, network, and throughput capacity. One of those capacity limits is called max connections. Now jumping into connection management, each instance allocated in DocumentDB cluster comes with its own connection limits too. Client applications that are running on EC2, containers, or Lambdas have to open a connection with DocumentDB before they can perform any CRUD operations. These are a list of the instances that are currently supported with their corresponding connection limits, cursor limits, and open transaction limits. Let's take a look at T3 medium for an example. Let's say my write API can take up to 500 milliseconds on an average. With T3 medium, I'm allowed about 500 concurrent connections as it's shown in the table. Then the maximum throughput that I can achieve with this calculation is about 1000 inserts per second. There could be some other bottleneck I could run into before I reach that limit, but 1000 is the max I can get to because of the connection limit on the E3 medium. There are similar limitation on cursor, which is used when you're using things like pagination or transactions if you're using it in your application. The biggest instance, as is shown at the bottom of the list, is 16x large that we support at the moment. That instance can support up to 30,000 concurrent connections at max. Now let's talk about some of the generic best practices around connection management with DocumentDB. As always, it is always important to correctly measure the impact of connections on your system. These 4 CloudWatt matrix will cover the ground at the high level. Instance memory is responsible for buffer caches, index caches, and it is also responsible for open connections. In an unlikely event, you may have thousands of connections open, which are just occupying memory, which could else be used by query operations. In some cases, this can cause your instance to swap or restart, or slow down in some cases. Amazon DocumentDB allows you to monitor maximum number of open connections on every instance using a special matrix called database connection max. We will monitor this when we run our load test today using artillery. Similarly, for cursor and transactions, we'll have database connection database cursor max and transaction open max. In your connections to DocumentDB, you can specify read preference equals secondary preferred, which automatically balances your read traffic among read replicas. This means that you have more read capacity available in a 3-node cluster that your read traffic can be redirected to. Primary instance is now free from any of the read interferences since you have the secondary preferred mention in your connection. Your read would be redirected to replicas first. For transactions, it is always advised to commit or abort the transactions after they're complete. Leaving transaction in an incomplete state ties up database resources and can cause write conflicts. It is recommended to keep transactions to the smallest number of commands needed. If you have transactions with multiple statements that can be divided into multiple smaller transactions, it is advised to do so. This can reduce the likelihood of timeouts. Always aim to create short transactions, not long-running reads on DocumentDB. You should also test and adjust your connection settings that matches your workload. Connection timeout MS is the maximum time the driver waits before the new connection is attempted and is stopped. The value of this setting depends on your network infrastructure. Because DocumentDB runs on VPC only setup, the clients are part of the VPC. The connection timeout should not exceed the default value of 10 seconds. You should also think about bringing it down if your query's SLAs are 3 or 4 seconds at max. Now let's take a look at the same topic of connection management, but this time with Lambda functions. In layman's term, Lambda is a piece of code that is running on a certain set of allocated resources. The first time you invoke your function, Lambda creates an instance of a function that runs its handler method to process the event. When the function returns a response, it stays active and waits to process additional events. If you invoke the function again, the first event if the first event is being processed, Lambda initializes another instance, and the function processes two events concurrently. As more events come in, Lambda routes them to the available resources and creates more instances as needed. When number of instances decreases, when number of Lambda concurrently running decreases, Lambda stops unused resources to free up scaling capacity for other functions. Now there's a limit of how many concurrent Lambdas you can run per region. It is usually set at the account level. For US East 1, it is set out to be at about 1,000 concurrent Lambdas by default. This limit can also be requested to increase if that's what your workload needs. Now, 1,000 concurrent Lambda, that sounds good, right? So what's wrong with that? What could be the bottleneck with this? This means that your app layer can scale horizontally. Well, good for Lambda, but with every Lambda, there can be a potential new connection that takes up memory. If Lambda is opening and closing connection very quickly, then it can cause a lot of context switching and consume all the CPU. Also, if the number of concurrent Lambdas goes beyond the connection limit of an instance, then the query starts to queue up and slow down. Eventually, you will start to see socket timeout and connection timeout error coming up. Also, your writer instances, you don't have ability to scale out. Only way you can allow more concurrent writes connections is by scaling up, which we saw that you can go up to the 16x large, which is the largest instance size available, which currently can support up to 30,000 connections concurrently. So what is the solution? It is as simple as allowing Lambda to share connections. With Lambda architecture, you can create your connection as a singleton outside your Lambda handler function. Then it is shared for the life cycle of that Lambda resources. Internally, compute and storage and memory allocated for Lambda stays active even after Lambda has finished executing. We will look at some of the code examples from our demo today for that. Now, it is okay to create connection pools since we're talking about connection pools here. In Lambda, as long as you understand your Lambda concurrency requirement. Now, there's always a potential of Lambdas kicking up too many containers behind the scene, which can create multiples of connection pools. Let's take up this example. In a connection pool of 100, it can end up consuming all 30,000 connections if your application layer just end up spinning about 300 containers. This is the largest instance, 16x large, that can support up to 30,000 connections. So what's the solution in this case? Now, there are a number of architecture patterns available to solve this problem, one of which is building your own proxy and connection pooling layer. You can manage that layer by using auto-scaling container group that can maintain ready set of connections that Lambda can utilize. Now, Lambdas can connect to that proxy layer through application load balancer, which can distribute the traffic based on the source or the application type. As a result of this, DocumentDB will have less number of concurrent connection open and will also give you better throughput per CPU as connections are controlled and reused by proxy layer. With this, what we would do is we'll jump onto the demo. The demo today will be using artillery.io, which is a popular load testing tool for APIs. Let me just go back and get out of this presentation mode and go to this browser. Now for the demo today, we'll be using this open source project that has API gateway, Lambda functions, and DocumentDB all set up as part of the CloudFormation template. This project is also available on GitHub that you can go back and set it up on your own account. And it sets up the required permissions, security details, secrets manager, and it asks for a simple question on what you exactly need to be set up. It's going to take you about 15 minutes to set it up on your account. For the demo today, I'm not going to do that. I've already gone through the trouble of doing that on my account. What I'm going to do is go back to AWS console, go to CloudFormation, and show you the stack, what it looks like after it's done setup. You'll see the stack name called DocDB REST. And within that stack, you'll have this output tab that has list of output that for the resources that were generated. For example, it has the API, which we'll be using for our CRUD operations. It created the Lambda functions, the authentication Lambda for basic authentication. And then it also created the stack name for DocumentDB called DocDB REST. Let me just go there and show you that as well. This is the database that was created by the CloudFormation template. It has 3 instances, 2 of which is replicas, 2 and 3, and doc.test is my primary instance, which we would be using for writes. Now let's try to connect to that. For connection, what I'm going to do is I'm going to open one more instance of console and start Cloud9 environment by clicking on this button. I've already created a Cloud9 environment in advance. In fact, that's what I used to set up my CloudFormation template on my account. What I'm going to do is I'm going to go back to this DocumentDB dashboard and download this PEM file by clicking on this copy button here. And Cloud9 environment gives me ability to edit my code in an IDE, and it also gives me ability to run a terminal for command line access. Now I have this RDS combined CA file downloaded. What I'm going to do is I'm going to go back to my second command and connect to DocumentDB using this shell command. My Cloud9 environment is already set up with Mongo client setup. So I should have the Mongo client already installed. If I do this, it's going to ask me to enter password for the DocumentDB cluster that I entered at the time of my CloudFormation template. As you can see, I am on the command line console for DocumentDB. The collection that we'll be using is called, database that we'll be using is called user. And within user, I'll be using a collection called profiles. Now, this profile already has some data already loaded because of my previous test. So what we can do is we can just wipe that now to make sure we are starting fresh. There you go. Now, let's start by setting up our project for the load test using artillery. We'll leave this terminal open. And what we would do is we would go back to our project and these instructions, which ask me to set up a special variable called URL base. If you follow the instruction all the way to the top, you'll look for a variable called URL base, which needs to be set up as a variable that we'll be using for the demo today. What I'm going to do is I'm going to copy this part of the command, URL base, go back to my terminal at Cloud9, create one more terminal, add URL base equals the output of my CloudFormation template. In this, I'll find the API gateway endpoint that we'll be using for CRUD operations. And I can find that in my output section. This API route is what we would be using to set up my URL base. Now, once this is set up, let's make sure it is there. We'll be using this endpoint to perform our CRUD operation. Let me do a quick demo of that using command line first. Now I can use a command like curl expert URL base. And then the way it works is I already have a Lambda function set up that creates dummy data using Faker library. All I have to do is supply a ID that would be used to ingest the data. What I'm going to do is I'm going to give it a simple ID called PR1000. And it said that PR1000 is inserted. And I can now check this same thing by doing a get command on the same method, on the same URI. Let me just do that. And it gives me this record that was generated by this Faker library called Grant Hunter. This record wasn't there before. Now, just to prove that, I'm going to go back to Mongo console and run this db.profile.count one more time. It gives me one record, as well as I can look at this record by running the find command. Now, we'll be using just this simple API of doing get and put to run our load test. Now, let's get back to the GitHub project. I've already took the liberty of downloading this project to this DocDB rest directory. What I'm going to do is I'm going to open this code app.py in editor just to show you what exactly it's doing. Like I said, it is doing a simple operations of get profile and creating a profile through this Lambda function. It handles just two functions, get and put, nothing else. It actually is creating a connection outside of handler. Since this is my handler function, I'm actually creating the client at the top. When I get the credential, this function would make sure that it only creates a client if the client is not available yet. So that's how you can handle and cache connections at the handler, outside of the handler in your Lambda layer. Now, this project also comes with this directory called load test, which is pre-built and set up to run your load test. Let me show you the content of that. It comes with a file called package.json, which is essentially your Node.js dependency package. All you have to do is run a setup, and it would install all your required dependencies. This also comes with sample test, which we will be modifying to run our test. Now let's go to another terminal, or maybe we can use the same one that we already created. Go to docdb rest, load test, and all I will do is I'll run this command called npm install. This will install the tool and library needed to run artillery.ai. As you can see, it did not take that much time. So what I'm going to do is I'm going to go back to my sample test.yml file, and it says that this target needs to be replaced. It is also using a JS file that generates a UUID. So every time we run this test, it's going to create thousands of threads, and every thread would have a different UUID that be inserting data with. The flow of this test is that you'll be doing a simple put, like the way we just demoed using the command line. Then it would wait about half a second, and then it will do a get. Basically, for put, it should use the writer instance, and for all the gets and reads should come out from your secondary instances, which are reads. which are replicas. Now let's work on changing this. What I'm going to do is I'm going to go back to my CloudFormation output stack again, copy this endpoint one more time, and go back to sampletest.yml. After I do this, I can save this, go back to one of my open terminals, and run a command called artillery, run sample test. And it's going to kick off the test that would start sending traffic to my DocumentDB cluster. Let's start that right now. While this is running, let me show you. This test is set up to run for about 2 minutes, 60 seconds, with the transaction rate about 5 transactions per second. It means it's going to do 5 inserts and 5 reads. And then after 60 seconds, it's going to ramp up to 10 requests per second. So not a big load, but just wanted to demo how is it done. Now let's go back and look at the status. As you can see, the test has been progressing. And while this is running, what I'm going to do is I'm going to set up my dashboard. It's always good to monitor this test while it's running. So I'm going to go to another instance of console, go to CloudWatch, and I'll start creating a dashboard for myself. I'll call it DocDB REST test. Within that dashboard, I can add widgets. I'm going to start by adding widgets for all the CloudWatch metrics. I'm going to start with lambdas because that's what we learned, that lambda concurrency is important. So I'm going to enter concurrent lambda. I'm going to select function name, and my function name is DocDB REST because that's what we'll be using for most of the critical operation. And I'm going to select this is a metric called concurrent executions. Add this to graph and create a widget. Now this is telling me that they're already workload running, their concurrent lambdas executing. We looked at that from our load test already. What I'm going to do is I'm going to adjust these settings to last 1 hour. And I'm going to change statistics to maximum for reporting for every second. And I'm going to update the widget. Now this is giving me that at the present, I'm getting a concurrent lambda execution for about 10 lambdas at max. You see that it has reached 10 at some point, but it's not going beyond that because that's the number of threads that we are sending in. Let's do one more thing. Let's add one of the metrics for DocumentDB, database connections max. What we would do is we would add it for both our readers and writers. Let's start by adding just the writer for now. I'm going to do the create widget one more time, and I'll edit that, set it to last 1 hour, change it to 1 second, and statistic can be changed to the maximum. And this updates the widget. Now, this is giving me an idea of what is the number of maximum concurrent connections open at the DocumentDB level. This is the test that we recently run. The previous peaks are from a previous test that I've been running and testing with. But this is the test that is currently being ramping up. And likely it has been finished already since the test was only for 2 minutes. I'll go back to my Cloud9 environment just to verify that. As you can see, it sent about it has all the statistics for the test I ran. I have the mean, median, max, P95, and P99 response time from the workload that I have in place. It has the status code for all the requests and the total number of requests actually that went in. So this gives you an idea on what is happening at scale on your cluster. I can ramp up this workload to thousands of transactions per second. And at that time, I'll start to figure out if I'm running into any of the concurrency issues with my APIs. If Secrets Manager is not able to send data to DocumentDB cluster quick enough, or if the Lambdas are not concurrently invoking. It's a good way to run your test and really analyze where might be a performance bottleneck. What I'm going to do is I'm going to go back to my CloudWatch alarm one more time, refresh this. So this is really the statistic that we'll be getting. In addition to this, you should add other metrics that you might be required to monitor at the same time and create a dashboard for your application itself. Now with that, what I'm going to do is I'm going to go back to our presentation and go back to the conclusions from the session today. There are a number of tools available to load test and stress test your application. But the whole point here is that you should frequently test your application to know the limit of concurrency at every layer, whether it's an API layer, whether it's an application layer, or is that at the database layer. Next takeaway is really separating your reads versus write. We looked at one of the ways you can do that by setting up read preference to secondary preferred at your connection level. You should use bulk writes for large batch changes. Small documents with a batch of 100 in one bulk write is much more efficient than individual 100 transactions. Next takeaway is cache connections as much as you can, creating a pool at the Lambda layer. Caching connections outside your handler that gives you connection reusability among the consequent instance of Lambda invocations. And finally, after you've exhausted all the above options, deploy connection pooling through a proxy or a connection pool service built on containers. Now with that, I just wanted to thank you all for time and attention today. Using these techniques we covered in this session, we can build more resilient application for the cloud. As always, feel free to reach out in case you have any questions. Thank you so much for your time today.